The Feasibility of Small Modular Nuclear Reactors by Luke, Chris, Paul, and Armand. Small modular reactors, also known as SMRs, are touted to be the future of nuclear energy. SMRs operate on the same basic principles of standard nuclear reactors. However, they take up a fraction of the size and include their own passive and active safety systems, which allow them to operate in more versatile locations. Their modularity will allow them to be factory built and transported to a plant for installation. Unfortunately, SMRs are still in the development phase and have yet to live up to these expectations. Only 2 operational SMRs exist, both of which are in an offshore plant in Russia. It is unknown if other countries will adopt SMRs due to licensing and capital issues. Economically, SMRs are an expensive, work-in-progress energy source that can produce reliable power, but not cost-effectively. As the technology advances, they may become more viable for energy generation in the future, especially once they can be mass-produced. But at present, they are expensive, and future-facing projects are liable to cost increases. The environmental impacts from SMRs are not definitively only good or only bad, as there are both advantages and disadvantages, with some being big and some being small. As technology grows and public opinion shifts, there is a high likelihood of the majority of environmental negatives of SMRs being phased out. The public does not have an opinion regarding SMRs, as most people have never heard of them. As of now, what side someone takes regarding them is mostly dependent on their opinion of nuclear power. In 2019, Washington State passed the Clean Energy Transformation Act, guiding the state towards a clean energy future by 2030. SMRs are expected to play a role in this future as a part of a national effort by the U.S. Department of Energy in collaboration with X-Energy and TerraPower. The reason for SMR's current existence in operational power plants is questionable, as they have yet to become the better choice economically, environmentally, socially, and politically when compared to conventional nuclear reactors, as they are expected to be. Thus, we would not recommend investing in them until they have advanced sufficiently to meet those expectations.
So what exactly is the power source known as the small modular reactor? To quote-unquote boil it down, it is a nuclear reactor that operates on a smaller scale compared to traditional nuclear reactors. This means that while it has a smaller power production, the system itself also takes a much smaller area. Now, the real draw for this form of energy is the modularity of its components. Modularity means, in this instance, that the components are to be prefabricated in a factory setting and are able to be shipped out onto a site and then be installed on site. Or, in some other cases, the entire system can be prefabricated and just installed. No need for any other integrations into the systems other than connections with existing power sources. This is meant to be a much faster and smaller process as opposed to how involved and tedious the typical nuclear energy reactor systems can be. With this process, a handful of designs can be approved and rapidly produced and transported to as a single piece and installed wherever need be. Now, how do small modular reactors work? Small modular reactors use nuclear fuel, typically uranium-235 or thorium. This is enriched and contain a higher concentration of fissile isotopes. These isotopes are atoms that split apart, releasing a larger amount of energy in the form of heat. Now, within the reactor core, control rods are made of materials such as boron or cadmium and are inserted or withdrawn to regulate the rate of the nuclear reaction. When the control rods are fully inserted, they absorb neutrons and slow down to stop the fission process. During fission, the nucleus of a fissile atom, like, again, uranium-235, splits into smaller nuclei, thus releasing a tremendous amount of energy in the form of heat. This heat is absorbed by coolant, typically water or molten salt, and are circulated through the reactor core. The heat absorbed by the coolant is transferred to a secondary loop, where the liquid comes into contact with water, which boils into steam. This steam is then directed to drive a turbine connected to a generator. As the steam flows through the turbine, it causes the turbine blades to spin, thus converting the thermal energy into mechanical energy, thus creating electricity.
Now let's talk about where small modular reactors can be implemented. Unlike large conventional reactors, which are quite large and take a lot of planning to decide where they can go, SMRs can essentially be deployed in places that are not normally accessible by large power plants or just areas with little space in general. So for example, if you have rural communities or just a small group of people living quite far away from civilization, and then where they have little to no transmission lines to the main power grid, SMRs can act as their own independent small-scale grids that can help power their energy needs without having a large cost associated with either making a big power plant nearby or just simply connecting them to the main grid.
The history of small modular reactors. The concept of SMRs dates back to post-World War II United States, when the military was experimenting with small reactors for use in combat vehicles. Nuclear subs were the only fruit of this labor, as they could not scale down the reactors enough to fit in most vehicles. The Army also researched small reactors as generators for their bases, particularly remote ones. However, the expense of this research led to diesel generators being used instead. In 1955, the U.S. Atomic Energy Commission funded 4 small reactors for rural areas. These reactors were subject to major delays and cost increases, and only one of the reactors operated for more than 3 years. The only reactor that lasted was the La Crosse boiling water reactor, which operated for 18 years. It was decommissioned because its operating price, and thus its electricity price, was too high. The first modern small modular reactor was invented at Oregon State University in 2007, which coincided with the founding of the US-based SMR company NuScale. Who is currently working on small modular nuclear reactors? There are currently about 80 SMR designs in development in about 12 countries for use for heat, energy, desalination, and steam. The only currently operating SMRs are found in the Russian floating nuclear power plant called Akademik Lomonosov. This plant was launched in May 2020 and has 2 SMRs that each produce 35 megawatts of electricity. It is currently located in the isolated Arctic port town Pevek in northeastern Russia. In 2023, China installed the 125 megawatt core of the first onshore SMR. Once operational, it is expected to produce 1 billion kilowatt hours of electricity per year. It is anticipated to be completed in 2026. SMRs are in the process of being implemented in Argentina, Canada, China, Russia, South Korea, and of course, the United States of America. All these projects are in various stages of completion.
The question regarding why do SMRs exist is actually more intricate as it involves cost reduction, lower nuclear waste, and production of cleaner nuclear energy. Now, the question of why do SMRs exist is a question without many answers, as SMRs are not used commonly. For one, the space needed for construction could be reduced significantly, and construction costs could also be reduced. The environmental benefit of an SMR is that it produces less amount of nuclear waste due to less power output per SMR. Lastly, the time needed for construction would be reduced due to the less amount of construction needed. SMR should be a great alternative from the standard nuclear reactor based on the information, right? No. The SMR's less amount of nuclear waste is not a good enough argument, as it produces less amount of power which to produce enough power. You would need many SMRs which are not both cost effective and waste effective. The safety concerns regarding SMRs are not much of a safer option than standard nuclear reactors. SMRs use a passive cooling system which dissipates heat with a very low energy consumption. However, this passive cooling system needs to be accompanied by an active cooling system as a countermeasure if the passive cooling system would fail, which just adds to the cost.
Now, on to the topic of how much energy small modular reactors could provide or save. Typically, SMRs provide energy in the range of about 20 megawatts to 300 megawatts of energy, which doesn't seem like a lot to some, but the minimum of 20 megawatts is enough to power around 20,000 homes. If we go to the savings for land, SMRs have actually quite a big advantage. According to the Nuclear Energy Institute, the same amount of energy produced from around a typical conventional reactor is the equivalent of 3 million solar panels, or about 430 wind turbines, which, as we can see in this image here, is quite a lot of land. Now, although this comparison uses a large reactor compared to an SMR, the same equivalency holds, although in a smaller scale, but it's still quite a lot of land if you consider that a megawatt of solar energy, for example, takes up around 4 to 6 acres of land, while the average size for an SMR is only about a grain silo worth.
The economic theory of SMRs. SMRs are smaller than conventional reactors, and they don't have to be designed for the location. They will be able to come prefabricated once there are operating production lines. This means that they will have faster construction times and are less likely to be subject to construction delays. They typically only require refueling every 3 to 7 years, compared to the 1 to 2 years of conventional reactors. However, SMRs are only in the development stage, so this theory has yet to come to fruition. The present economic reality of SMRs. At present, SMRs are more expensive to build than traditional reactors. The economies of scale make larger, higher power nuclear reactors more cost-effective than smaller, lower power ones, because they don't require very many more resources, but can produce much more power. An example of economies of scale given by the article The Forgotten History of Small Nuclear Reactors says, quote, "For instance, a 400 megawatt reactor requires less than twice the quantity of concrete and steel to construct as a 200 megawatt reactor, and it can be operated with fewer than twice as many people." Unquote. Also, many projects on SMRs have been subject to major cost increases or project size reduction. Here are some examples of changes made to SMR projects. The cost of constructing the previously mentioned academic Lomonosov was projected at 9 billion rubles in 2006. This is roughly $170 million. The actual cost was roughly 37 billion rubles, which is about $700 million. The American SMR company NuScale was working with UAMPS, which is the Utah Associated Municipal Power Systems, on a power plant with 12 50 megawatt reactors. The estimated price for this project in 2020 was $6.1 billion. This estimate included construction, 40 years of operation, decommissioning, and was adjusted for inflation. The project received a $1.4 billion award from the Department of Energy in 2020. Despite this, in 2021, NuScale cut the size of the project from 12 reactors to 6. This change, combined with cost increases, resulted in the project being terminated in 2023 after several member municipalities of UAMPS backed out. SMR operation cost estimates. The power cost of the UAMPS project was estimated at about $58 per megawatt hour in 2020. In 2023, it was increased to $89 per megawatt hour. Tacoma Power's IRP estimated a range of $40 to $130 per megawatt hour for SMRs. This is not great when you compare it to the estimate of $20 to $50 per megawatt hour for operating wind and solar plants. Due to their high upfront and operating price, it is not cost-effective to use SMRs as a demand-matching power source, which was one of the primary reasons that they were considered. Hopefully, sometime in the future SMRs will be produced by factories at a reasonable price, but until then, they are not economically viable.
Moving on to the environmental impacts of small modular reactors, there is quite a lot of things to consider for nuclear energy in general. Some things are good, and some things are bad. Unfortunately, nuclear energy can't really be divided into one set side of being good or bad, and ultimately that often ends up on someone's opinion to decide if it's good or bad for them. But regardless, we'll go over some of the key impacts that nuclear energy has. For the bad effects, we have fuel disposal and how it's handled, and the local environmental effects of having reactors nearby. For the benefits of nuclear energy, we have the good fuel density and the near zero carbon release from the power production cycle as a whole. Going into depth for the benefits, we can see that nuclear fuel pellets actually have quite a large amount of energy density compared to other forms of energy. Around an inch big uranium pellet holds the same amount of energy that would require 17,000 cubic feet of natural gas, 120 gallons of oil, and around a ton of coal. Another thing that's good is that SMRs would only need refueling about once every 3 to 7 years, compared to the 1 to 2 years for conventional reactors. Some SMR designs actually would require refueling only once every about 30 years, which is an even better benefit for the environmental impact. However, we can't ignore the risk that comes with nuclear energy. A large problem is actually with waste disposal, since we don't really have any definite procedures on how to handle nuclear waste. As of today, we can just store it in underground locations and wait indefinitely until we have some sort of solution as to reuse it or dispose of it safely. Another issue is that rising temperatures and changing weather conditions around reactors can actually cause operations for them to be scaled back or even shut down in some cases. This can cause problems because being shut down and then restarted can actually result in more fuel being used up, which once again leads to more fuel disposal and more problems for the environment. Another big issue is actually the cooling water used by the reactors. When it gets released back to the environment, it's at a quite high temperature and sometimes mixed in with some unpleasant things for the environment. And this can actually cause local damage by damaging the wildlife and the ecosystem as a whole. And this can cause issues for quite a number of years unless it's resolved.
The social impacts regarding small modular reactors. The people's opinions regarding small modular reactors is unknown, as there is no data available to support for or against it at this time. However, based on this data associated with both nuclear reactors and nuclear energy, we notice a split in people's decisions in the US. First off, the public doesn't really know what nuclear energy is, how it is produced, and how it can be used without drawing very extreme conclusions. There are a lot of people worldwide that do not support anything nuclear due to many political and environmental problems that surround it. Some examples are the Chernobyl nuclear disaster and the Fukushima nuclear accident, which made an indent into people's thoughts about nuclear. Even the treatment of the nuclear wastewater into the ocean caused outrage worldwide, as the people did not understand what it does, but associated the word nuclear as such a dangerous term. Finally, nuclear reactors operate worldwide, with many countries having more than 5 each. People tend to associate nuclear power plants with the causes of cancer, though, and other human health conditions, which causes the public to stay away from nuclear. The public's opinion regarding SMRs is unknown at the time, as stated earlier, as we do not have sufficient data regarding SMRs as a topic. However, knowing the word nuclear is associated with SMRs could cause pushback from the public due to disaster events in history. Also, nuclear energy is still not favored, as the alternatives, such as wind and solar energy, are both clean and environmentally superior, as they produce little to no waste. The advantages regarding SMR's equity is linked to the prices of nuclear energy, and compared to alternative energies, as shown, nuclear energy would be cheaper than coal or fossil fuels. However, it still loses to natural gases produced from those power plants. Now, the disadvantages of equity regarding SMR is that the initial capital cost is not as cheap as it sounds. As a reference, NuScale announced that its planned price of electricity from the Idaho plant project had increased from $58 per megawatt hour to $89 per megawatt hour. That's more expensive than most other sources of electricity today, including solar and wind power and most natural gas plants.
Now, what is the current influence that legislation has on the production of small modular reactors? As of 2019, Washington State has passed the Clean Energy Transformation Act. This act strives to transition the energy production in Washington State towards greener alternatives. Federally, the U.S. government has partnered with X Energy and TerraPower, investing $80 million towards each company towards a small modular reactor production and research. They are seeking to implement the technology as soon as 2030.
In conclusion, SMRs have the potential to be a good option for power generation. However, with current circumstances, they are not viable because they have yet to reach the stage where they are truly modular, resulting in poor economic value. Because of this, we would not recommend investing in them at this time. What we would recommend is keeping an eye on their progress and being prepared to invest once they are ready for mass production. Thank you for watching.